Oops, we're on the wrong stuff here. I need to go to here. There we go. Sorry about that. And then you had to hear that annoying clicking. All right, let's take a look. This is just to help you a little bit with that hockey problem. And I made a mistake when I did this video before. All right, this is my third time. Third time's a charm. It's always that way with the first one. All right, so here we go. Now let's take a look. We got a baseball. I'm going to do it. This one's going to be a little bit more complicated because we've got an initial velocity. And in the problem that I'm helping you with here, you didn't have an initial velocity, but notice, and it's going to the left, which is in the negative x direction. So let's just say this Major League Baseball is coming in at negative 35 meters per second, because that's about what by the time they reach home plate, they've actually, due to drag and all kinds of stuff, they've actually slowed down. Their average speed when they leave, whatever, we might talk about that later. Then boom, big collision. You know, like they do in cartoons, they always have stars and stuff like that, and there's big collision, boom. Then it takes off. We're going to just have it going in a straight line here. At V final is positive 40 meters per second. Let's keep it simple. All right, and so here we go. So the impulse, since it's a vector, is going to equal the change in momentum, which is equal to the mass, and the mass of the baseball is 0.145 kilograms, times the final velocity, 40, minus the initial, negative 35. Okay, I don't put it in the units when I actually start doing the math here. So we've got 0.145, and this is kind of complicated. I mean, we're pumping up the volume here for a 100 level science class. All right, with what's going on, and with the math that we're doing, and to invoke the spirit of one of the greatest math teachers of all time, Jaime Escalante, we've got it negative minus negative. Negative times a negative is positive 75. And so when we do that calculation really quick, we get about 10.875. Get about 10.875 kilograms meters per second. Now, momentum doesn't have a fancy word like newtons or joules or anything like that. It's just momentum, and it's in kilograms meters per second. Another fancy way to say it is Newton seconds. Because look, if I have kilograms meters per second squared, multiply that by a second, by a unit of a second, then the second squared down here, so the newtons, so you can call it a Newton second if you want, but I just leave it at kilograms. It's momentum. All right. But now, so what's the average force of that bat? Delta T. That's also equal to this change in P, which we found was 2.875. Okay. And so delta T actually for a Major League Baseball collision is this, 0.0011 seconds. 1/1000th of a second. It's amazing the technology that we have now to be able to get that kind of time down. That's why with the hockey problem earlier, I said, my alarm just went off. You know why? Because I've got to go see grandbabies in California, and I've got to get my Southwest boarding pass. 24 hours from now, we're taking off. So I've got 4 minutes here. I better finish this. All right, so delta T. So I wind up with, so if I want to find the average force, then I get this. 10.875 divided by 0.0011 is equal to, now all I got to do is find my stupid calculator here at Fibber McGee's closet, and I'll let you see this calculation if it shows up. Oh yeah, that's going to show up nice. See, I did this wrong first. First, let's say 0.001. So let's get rid of that. So we got 10.875 divided by 0.0011. Boom! 9,000, almost 9,900 newtons. Almost 9,900 newtons. Whoa! That's a lot of force. That is a lot of force. that's happening. That's a huge average force. That's the average force. Now at the height of the collision, it's around 11,000, 12,000 newtons. It's a tremendous amount of force. Okay. All right, so there you go.